In this video I'm going to be going through the three-force method. This is the second example on the topic from Engineering Studies Definitive Guide, Volume 1, second edition. It's example 2.5 on page 58. The actual diagram looks something like this. And what we're being told to do is find the reaction force in this cylinder and to find the force in this pin. Now the thing is, we don't know the angle of that pin, so that's what makes this question difficult. We're going to look at what we would do if we did know the angle of this pin, and then we're going to solve it using what we call a three-force method. Now the thing I want to point out is, there's a transferability of forces, that writing this is the same as writing that. As far as we're concerned, as long as it's in the same angle and it's applying at the same location, we don't really care if it's above or below. For me, that looks more like a natural beam, but I'm going to show it the way it's shown in the book. The point I'm saying here is that we have this diagram here, but what I want to try and do is I want to try and focus in on the information that matters. So what we know is we have a force acting on the cylinder, and we know that there's a force in this pin. And I find that if we take out this diagram, it becomes much easier to follow. So we're going to call this our free body diagram. We've taken out the stuff that might distract us or might make it more confusing. We're just focusing on what matters. Now, imagine if we had a diagram that looked like this. If we had 12, 30, and we'll call this 15 degrees. Okay. If I had my force diagram looks like this, and I tell you that this is 30 degrees, and I tell you that this is 15 degrees. If that's 30 and 15, what are we going to get? What's the value of this angle here? It's a complementary angle, it means it adds up to 90 degrees. 60, excellent. Okay, what's the angle of this here?
75.
Okay, so this is 90. This is 90 plus 15 is 105. And then what's this value here? Okay, this angle here is going to be 15. Can anyone tell me why it's 15?
Angles add up to 180.
Yeah, the angle sum of a triangle is 180. Now, if I'm then told, I'm just going to redraw that triangle now. It's not perfect, it doesn't need to be because we're just using it as a diagram. If I told you this is 1200, 105 degrees, 60 degrees, and let's say I wanted to find this side here, FP, right? How would I find FP? Well, what I could say is that using the sine rule, I know that sine A over sine A equals B over sine B. Yeah? So for us, what we're going to say instead is we're going to say the unknown that we want to find is FP over sine 60 equals 1200 over sine 15. That means if we multiply both sides by sine 60, those two cross out. We can rewrite that as FP equals 1200 sine 60 all divided by sine 15. Okay, can anyone type that into the calculator for me? Sine 60 divided by sine 15. Oh. Okay, I just got a number that was negative, so that was a good chance that I had not hit my calculator too quickly. So that's again me using estimation to figure out things. Divided by sine 15. I get 415, sorry, 4015, so equals 4015 newtons. And it's 15 degrees. Except the problem is, it's not really at 15 degrees. We just made up this number. So the question is, how do we figure this out without making up this number? Well, there's complicated ways we can find that angle. right? The sort of thing we do in year 12. But in year 11, what we're going to do instead is we're going to use our tool, our handy dandy protractor. Now you cannot really solve this question using this method without a protractor. So what we're going to do is we're going to follow the 3-force method. The 3-force rule has, I've got 4 steps here. The first thing is we have to figure out, does the 3-force rule even apply? Well, first of all, how many forces do you think we can have for this rule? The 3-force rule, how many forces do you think we can have in the 3-force rule?
3.
3 is the answer. Okay, the thing is, for it to apply, if you have 3 forces, they either need to be all parallel, or all 3 forces must meet at some location. Right? That is the 3-force rule. Either they're all parallel or they all meet at this point. So we call that a concurrent set of forces. These ones here, where they're all parallel, they're all non-concurrent. Where they all meet in one spot, they're all concurrent. That means they all meet at this one location, right? The point of concurrency. So the first thing we need to do is we need to see, are there 3 forces? Are they concurrent? We know they're concurrent because either they're all concurrent or they're all non-concurrent. So we can look and see if 2 of the forces or the 2 forces we're given, if they're parallel, we know that we don't use the 3-force method. Okay. Now that we've figured out that the rule does apply, we know that there are 3 forces, and the 2 forces that we have angles for, we know that they're not parallel. What we need to do is we now need to find the point of concurrency, right? POC. It can stand for other things, but we're going to go with point of concurrency. So what I do is I extend my lines and I find where they meet. And I write here, OMG, point of concurrency. You don't really need to write the OMG part. You don't even really need to label it, but you know it's going to show me that you've used a strategy to solve this question. So we found the point of concurrency. We don't really have enough information though yet. What we need to that doesn't straight away find us this angle. What we need to do is we need to say, well, if these 2 meet at that location, if 2 of them are concurrent, they must all be concurrent. There's 3 forces. If there's 3 forces, they're either all concurrent or all parallel. These ones must be all concurrent. That means that this force here must meet up at that location. So how do I find the angle of this force? I go, well, it must go here, and it must go there, and it's got to be somewhere in between those. And I draw a line that meets up. And I can call this angle here is my theta. This angle here is my theta. Okay. So, now that I've got this angle, I know that my force is going to be also at that same angle. Like that. Now that I have these forces, I can now draw my diagram. I can say, well, I'm going to have 1200 going down. And what I then do is I add these other values tip to tail. There's different ways we can do this, but basically what I want to look at is I want to look at my vectors. I've got 1, 2, 3 vectors, and I want to slide these arrows across until I can make them add tip to tail. When I say tip to tail, you notice that I draw my arrow normally in the middle, but here the pointy part of that arrow is touching the feathery part of this arrow. The pointy part of this arrow is touching the feathery part, pointy, feathery. Yeah? They're going around. Another way of saying that is that this one here, is it going clockwise or anti-clockwise around this triangle?
Anti.
So they're all going anti-clockwise. Yeah? They have to, if they're all adding up to 0, if they're in equilibrium. I mean, yesterday we talked about, or last lesson we talked about the difference between equilibrium and resultants. If they're in equilibrium, if all these forces add up to 0, they have to all be going in the same direction. Yeah? If they all add up to 0, they have to all be going in the same direction. So, Now, what I then do is I then measure this angle, right? And I say theta equals 17 degrees. So, if this theta equals 17 degrees, that's not 105, that's, what's the real answer? 107, because it's 90 plus 17. You okay with that? 90 plus 17, okay. 90 plus 17. Where did that 17 come from? Let's go over it again. Step 1, I found out whether or not my rule applies. There's 3 forces, and 2 of them meet up. 2 of them are concurrent. Once I did that, I found where those 2 forces meet up using my red lines. The next thing I did is I drew a green line that joined the point of the force that I'm looking for, and I joined up that with the point of concurrency we found earlier. What does that do? It helps me find the unknown angle theta. Then, once I know the angle theta, I can then draw a triangle where I add up all the forces tip to tail, and I just slide these forces along until I make this diagram. But you can see I have this diagram here, so that they're all going tip to tail, because in this case, these 3 forces are in equilibrium. It's not moving, so it's in equilibrium. That means all of these forces added together equal 0. So, if we add this plus this plus this, the gap from where we start and finish is 0. There's no resultant. Now, if we want to find FP, what did we say the rule was? We said the sine rule is A over sine A is equal to B over sine B. Where, for us, what we said is that FP over sine 60, that can stay, we're happy that that's correct. AP over sine 60 equals 1200 over sine 15. And so this is no longer sine 15. What is this value? So we've got 107 plus 60. 107 plus 60 is 167. So if I need plus what equals 180? What do I need to add to get to 180? 13, exactly right. So this here is going to be 13. Now, (1200) sine 60 divided by sine 13 equals, what is our answer? (1200) sine 60 divided by sine 13 equals, second time I did that. I got to type it, hit the enter in between. Sine 60 divided by sine 13 equals, I get 4619. Just checking I'm looking at the right side. FP, 4619.
Yeah, I got that.
Let's see what the book says. Yeah, FP 4619, and that's in newtons, so we can give the answer as kilonewtons, as 4.6 kilonewtons is what the book finishes on. Okay. Now, what we're also allowed to do is we're also allowed to just draw the diagram. We're allowed to use a protractor, and what we can do is we can say, there's a couple of ways we can do this, and it's about the way that you feel comfortable with. I could say, well, I already have this force and this force are already touching. Yeah? If I use this red line that I've just drawn up earlier, if I use this red line, I could say, well, this force and this force, they're already going tip to tail, aren't they? Yeah? They're going clockwise, but that's okay. So what I'm going to say is, well, FC, I don't know, but this one here I'm going to draw to scale. So what would be a good scale for me to use for 1200 newtons? Well, I look at my ruler and I say, well, 120 newtons looks about right. So I'm going to get this so that I'm going to draw 120 newtons. I just want to get my angle as close to right as possible, so that's why I'm fudging these things here, because I know the actual angle. So I'm going to say, and I've measured this, I've measured that value as 1200, but I'm using 120 millimeters equals 1200 newtons, yeah? Now the size of this one here, I don't know. I don't know the size of this one, but what I can use is I can use my parallel lines to be able to solve it. So I can say, well, if I draw a line that's 17 degrees from here, I'm just trying to get my angles right. Sorry for the delay. Feel free to skip. Okay, so that's a pretty big triangle, and you can see it goes over my other diagram. But that's a way that you can solve it. Now it's interesting to note that this diagram, I'm going to remove the stuff that's a distractor. I'm going to rub that out because I can do that. I can say, all I'm going to be left with is my force diagram. Okay. I know that this needs to be going this direction to maintain that, in this case, they're all going clockwise. And what I can do is I can now measure this line. Now it's obviously a pretty big scale, so we'll see if I can get this right. But 200, 400, 440, 450. Okay, so I get 450 millimeters, which at our scale, that should be 4,400 newtons. Now, we can compare that to what we calculated. What we calculated, and more accurately, what we calculated was 4619. But this here is pretty close. And to be honest, it doesn't even need to be that close. I will mark anything within 20 and even maybe 25% error as correct. So in this case here, we're off by a very small margin, and that's probably because I can see the answer. But I sometimes do this on the board, and I'm very wonky when I do on the board, right? Often I'm just guessing at angles, I'm just drawing the angle more or less. It's a lot harder to draw on the board with a protractor that looks like this than it is for you on the paper. But we'll do some class examples where we'll draw these ourselves, but the point is we can also draw in this manner. We can draw our diagram on the piece of paper, have a look at the way Copeland has drawn it in his book, and that will give you an idea of how you can solve these questions. So, just to wrap up, what we do, first thing we do is we say, does the three-force rule apply? What does it need to do for the three-force rule to apply? It needs to have how many forces? And what do those three forces need to? Well, the two forces we do know, they either need to do something or something. Either they meet up or they don't. For the three-force rule to work, we need to have them meet up. Why do we need them to meet up? So we can find the point of concurrency. Yeah, we find out where they meet. Once we find the point of concurrency, we can then find the missing angle, the unknown angle, by drawing our green line. Once we draw our green line, we can then either solve graphically like we saw here, right? Graphically like we saw here, or we can solve them analytically, but we're using the sine rule.